That way I'll have just an initial video of kind of like house cleaning of the course, and then let's start the lectures for today. So for today, the lecture is essentially, I'm going to talk about reinforcement learning, right? And reinforcement learning can be divided in maybe two areas. So I have a couple of links here that I'm going to show you. So this is the paper, the Siegler paper. Read that paper. I would recommend that you do, if there's one paper you read, is this one. Then I'm going to click on this link, Q Learning. And I think whenever you're trying to understand reinforcement learning, the topic of reinforcement learning, the best place to start is Q Learning, right? So I'm going to start with Q Learning. I'm going to go over this material today, and we're going to go through a simple program of how this works, because a lot of the ideas can be used for other things. So I'll go over this today, and also I provided the code here. So if you click on code for Q Learning, right, I provided this example, Frozen Lake, which is the example that we can try to do in class. And then if time permits, I just have another example that I did, just like I did some examples last week, where we trained a GPT to generate spammy text. Now I have an example to train a GPT to be better at solving math problems, but it's not DeepSeek yet, or chain of thought reasoning even. Is just something kind of in between. All right, so as we talk about reinforcement learning, so let's just go over a few notes here. So reinforcement learning can be divided into, I would say, two areas, like the Q learning approach, which sometimes these are called like value learning. And then you have another approach called the policy approaches. So Q learning and policy approaches. So under Q learning, we're going to have algorithm, the Q learning algorithm. So the value learning is Q learning. And under the policy approaches, we have PPO, DPO, GRPO, which is the new one that just came out. Okay, so these are essentially the ways that you divide reinforcement learning. I first learned about reinforcement learning through Q learning, so this is the one that we're going to discuss today, and what the idea is essentially here. This is related to games. Okay, this is how it started. I should say the history of Q learning and reinforcement learning started with games, started with board games, and so on. So, and this obviously, as you know, where I'm going with this is that for a GPT, we use reinforcement learning through human feedbacks, RLHF. And what we train is a GPT model. So we train a GPT using some kind of RLHF approach. And we use one of the techniques. So the techniques used in a GPT are essentially a policy approach. So policy. All right, so it's kind of like that. So the reason I would say why we're looking at reinforcement learning is this is how you arrive at training something like ChatGPT, but we want to start to understand a little bit how reinforcement learning works. Okay, so we're going to start with the basics. So I'm going to, let me close all this so I don't get, I'm going to stop that. This one, close that one, close that. Great. So let's go back to table of contents on Brightspace. And we are looking at reinforcement learning. And we're going to start here with QLearn. All right, so you guys have taken machine learning courses before. You essentially know that when you train a model, you give it some data, right? And so either like regression data, classification data, but you have some kind of annotated data. Even when you give a GPT, when you train a GPT, you would give it input text and output text. So for instance, the first sentence and the next sentence or something like that. And you're training data. Reinforcement learning kind of started with the idea that you were not really, you didn't have data. Instead, what you had was what is called an agent, something in an environment that is essentially that agent has a state in the environment. And then based on that state, it's going to select an action from a list of possible actions to take. And then once that action is taken, that action is basically like played in the environment. And based on that action in the environment, you get a new state. Okay, you get a new state, and that new state then provides information. Where did you end up? So for instance, let's take the idea of the very simple example of this game called Frozen Lake of reinforcement learning. So in Frozen Lake, it's essentially a grid, right? So this little grid, and this is the entire game. This is the universe of the game, because these are all the possibilities that you have available. So you start somewhere. So let's imagine that this is a mouse that needs to go over a frozen lake to find the cheese and eat it. So it's going to have a starting point. And then all the mouse can do is it can go left, up, let's say, up, left, right, or down. That's it. Those are the 4 possible actions. So then you have the mouse, it starts and it goes left. So that's frozen. So that means that it walks on frozen ice. So it's fine. Then it goes left again and it falls in a hole and it dies. So that's the end of the game. So another option is start, it goes front, it falls in a hole, it's over. But then it starts, it goes to the left, then it goes to the front, and that's fine. Then it goes to the left, that's fine. Then it goes to the left, and it falls in a hole, and it dies. All right, so that's essentially how the world here works. You don't have annotated data, things that you're correlating from one input to the other. What you have is really actions that you can take, and those actions take you from one state to another. And that state representation is complicated to create, okay? And so this same idea was adapted to GPTs. However, I don't want to mix that right now, and we're just going to focus on this original idea of reinforcement learning, just so that we can understand something at a very simple level that can then help you to have a better understanding of this. Okay? So that's essentially how it is. So again, I'll repeat. You from this game, you identify that you have 4 actions. You have a state which has to be encoded as this grid. So essentially what this state tells you is where you are in this grid, right? So if you were here, you were at this position, frozen, and then once you took an action, you went left, so you ended up here. So now you are at this position in the space. Row 4, column 2 versus row 4, column 3. So the rules of the environment, like, the information about where you fall, have to be encoded manually. So you set up the game environment. That's why we can use a library called AI Gym, which we will take a look in a second. And AI Gym is a nice library that allows us to play several games that are available. Okay. All right, so in this section, I will cover the topic of reinforcement learning. This is an area of machine learning somewhere between supervised learning and unsupervised learning. It has been extensively applied to recommender systems and AI-based games. Recently, it was shown that, and by recently, I mean like 2014, 2015, it was shown that a deep Q network using only pixels and game scores as inputs could achieve a playing level comparable to that of professional human gamers across a set of 49 Atari games. So back in 2014, 2015, they trained an agent to be able to play 49 Atari games. So those are Atari, if you remember, is from the 80s, and it's two grid or two-dimensional games. And so that's similar to this, because if you add a third dimension, obviously it's much more difficult. This is the citation for the paper, so it's Emney is the author. The main advantage of playing reinforcement learning, of applying reinforcement learning to games is that games are governed by rules, okay? You have a game, you have game states, the inputs, and actions, the outputs, that lead to new states and rewards. And the rewards are essentially the thing that you're trying to maximize. So in essence, like in when you were doing, your classification, training iris or MNIST, you're trying to minimize the error, essentially. Whereas in reinforcement learning, you can think of it as you're trying to maximize the rewards because you want to get more rewards. And there's got to be a rewarding system or mechanism. And that's really hard, actually. So it goes back to that idea that I said in RLHF of how do you reward a robot to let it know that it's becoming good at dancing salsa, right? So that's a really hard problem to solve. And that's where RLHF came. But initially here, since this was applied to just board games, when you're playing chess or any game, you take a move and it's somehow easy to heuristically set up a reward function. So anyway, you have a game, you have game states, the inputs and actions, the outputs that lead to new states and rewards, which are the objectives to maximize in the game. Because of this, no annotation is needed, and instead you rely on the rules of the game for feedback. All right, and this is instead of the annotated labels. So this is the essence, one of the important aspects of reinforcement learning. So in this section, I will cover this topic. All right, and I've mentioned this. Let's just elaborate a little bit more. The paper here, you can see it's in more detail. It's Emney 2015. Okay. So we'll go over some of the simple intuition. So what is Q learning, right? So Q learning, that if you start looking at reinforcement learning, it'll talk about these ideas of value learning, etc. But what you can think of it as just a table, essentially. Okay, you can think of it as, so I'll give you this idea. In its most simple form, most intuitive form, you're trying to learn a table between the state that you're in, right? So between the state and the action you should take for that state. So it's like saying, okay, if I'm in state 7, then I for sure should take action down. So this second action. So you can see here in the first row, for instance, I have these values. So for state 1, the Q value is 0.6. If I'm in state 1, the down action is 0.8. If I'm in state 1, the left action is 0.1. And if I'm in state 1, the right action is 0.0. So what this tells you is that the most likely or the best action to take whenever you're in state 1 is the highest value here. So that's going to be to go down. Do you guys see that? So if you're in in some state, for instance, let's say that you are Mm, yeah, here actually, right? So this is a hole, this is a hole, and you're in this position. So that action, the best action here is actually to go down. All right. And so that's really what you want to be able to learn. So this table essentially is the best way to understand this idea. Obviously, this table eventually can be modeled by a neural network. So it becomes more efficient. And that's called deep Q learning. So anyway, so Q learning tries to learn a value, the value of being in a given state S and taking a specific action from there. Okay, so that's the idea. So this example is a frozen lake, which the state of this is just this grid. So you have 16 is 4 by 4, so you have 16 possible positions that you can be in. If you notice in the table here, this has 16 possible states. Do you see that? So one way of thinking about this is that you're encoding the this this game as a vector, essentially. So this might be helpful to view in the code. So let me start up Anaconda just so I can give you a little idea. So I'm going to start Anaconda prompt. And I'm going to take a look also at the code in case I provided. So this is going to be the code that I'm going to look at. And it doesn't say what version of Python, so I'm just going to go with like, hopefully 3.7 will work. All right, so okay. So I'm here, BLS. I'm going to check out. Yeah, so I need to go back to our folder to navigate into, this is 530, CD, ITS 530. Oh yeah, 2025 spring. Okay, we are. All right, so we've done Hello World GPTs, in-class AI agents, small agents, and RLHF. I think that was the spam one. So here I'm going to create a new folder. I'm going to just call it RL Q Learning, actually. Q Learning. Okay, the DIR, there we are, ELS. Now I'm going to choose an environment on the environment list. So I have this environment, ITS Pi 37, 530, 2024. We're not using Hugging Face or any library, so I'm going to try that one. Conda activate I-37 530 537 530 2024. Okay. All right, there we are. So now I'm going to start a Jupyter notebook here. Okay. I didn't install Jupyter. Huh. Okay. give it a minute. Right. So let's do CLS. Let's try it again. See if we can get a Jupyter notebook. Or yeah, so we are okay. RLQ learning. I'm gonna hit Python 3. All right. Okay, so we have an environment here. So this is where we're gonna try to, you know, go over some of the ideas of the code. So the first idea of the code that I was looking at was this idea of the state. So the way that you want to think about it is this grid. So this is the easiest possible representation of states because it's a very simple state. You only have 16 possibilities. So 4 by 4. So you can represent the state as simply a vector that is, it's got 16 values. So most of these values are 0. So you can take a one-hot encoded approach of it to it, and then dot, dot, dot. And then you have one state that is 1, and then maybe 0, 0, and so on. So this would tell me that this state is, this state would be what? So there's 16 states. So it would be state 0. If it starts at 0, how did we have it in the notes? In the notes, it started at 1. So then it would be 16. So 16, 15. So this would be state 14. Okay? State 14, which essentially means that you would be, so this is 16, 15, 14, 13, 12, 11, 10, and so on. So then you would be in that state here. Whole would be your position in the state representation. If you make it to the state cheese, which is where you want to go, that would be 1, 2, 3. So vector with all zeros except for a 1 in the third position. So that's the state representation. Any questions about that, guys? So that's how you keep track of the states. And we'll see that as we start going into the code, but that's an important concept. This is really hard if you're doing this in 3D. Imagine if you were trying to apply this to a Tesla self-driving car. How do you represent those states? It's much more complex. Images could also be used, etc. All right, so let's keep going. So what is Q-learning? So Q-learning tries to learn the value of being in a given state S and taking a specific action from there. Okay, so that's essentially the simplest example of it is this table. So you are in state 3 and you have a set of fixed actions, and basically you're going to need to calculate the values so that you know which one to choose. That's something that initially this table might be all zeros or random, but over time, you're going to learn what these values should be. Okay? So that's the simplest explanation. All right, so Q-learning tries to learn the value of being in a given state and taking a specific action from there. As indicated, Q-learning has been applied to games. The best way to understand the algorithm is to analyze it from the point of view of a game. Here we will use Python's OpenAI Gym module to play games. So this is essentially like a library that you can use that has many games. And I'm pretty sure there's Atari and things like that, but we will just look at this very simple example. We will select the simple frozen lake game environment. Frozen lake is a game about crossing a frozen lake that has some cracks in the ice with holes. There's also wind, but we will ignore it for now. And there's wing sometimes that pushes the person crossing it. It's like a randomization that just flips you from one state to another. The game is very simple and consists of a grid that is 4 by 4, like so. So the objective is to get to the cheese without falling into a hole or being pushed by the wind into a hole. There are 4 moves, which are up, down, right, and left. There is only one reward, and that is to get the cheese, essentially. However, you only get that reward in the future by first taking several steps on frozen blocks without falling in a hole. Therefore, one challenge is that you have to state your objective in terms of several future moves. Okay. So, how do you figure out essentially how you get to the final outcome? But this was solved by a very smart person called Bellman. So this is accomplished using something called the Bellman equation. So we will see in the algorithm how using an equation called the Bellman equation allows us to compute these values in a way that after much playing and training, we'll have a good set of values for this. And essentially, you've learned how to play the game. Okay? So this is accomplished using something called the Bellman equation. The key to predicting these rewards is to know the associated reward given a current state and action to take. Okay, this is called Q mapping. So in fact, the rewards are actually the values in the Q table. So if this is the Q table and you have a given state and action, then the value in there is the reward that you're calculating. Okay. So you will need to know the reward, the current reward that you have that you're trying to modify and the reward in the future. For such a simple grid, we could just use a table. In this example, our table would be 16 by 4 because there are 16 possible states, which are the positions in the 4 by 4 grid. And there are also 4 actions. Now here's the trick. So since we know the rules of the game and the layout of the grid, we can populate the table and learn the Q rewards for each state action pair. So that's something that we can learn because the environment will give us this feedback essentially so that we can learn. So the main challenge is that we need to learn future rewards for future actions as we move through the grid. And this is where the Bellman equation will help. Think of the Bellman equation as a type of recursive equation that looks at the future state given a current state. And this is actually the formula for the Bellman equation, which this value reward is actually the current value of Q of the Q table at state and action. So I should have written this as this here. And then what you do is you take that current value plus an estimate of the future Q value given. So when you're at this state and you take an action, you're going to get the next state that you're in. So that's this value here. What is the future state? And then you're going to have all possible future actions. So you just pick the maximum one. So we'll see that in a bit, but that's essentially the idea of it. Okay, so this is so I'll let me rewrite this. Okay, so I'm going to go back to the Jupyter notebook here like that, right? So really, I can rewrite that equation as that, like that. So, it just starts with the current state, but you're at that state, you take an action in the environment, and the environment returns the next state. So I can just write next here. You see that? And then in the Q table, right? I can look up that next state, right? That next state, and I'm going to grab all four values for every single one of the actions. And then what the Bellman equation says is you just take the maximum of those, and then you add that value to the original one. So that's essentially what you're doing. It's like you have the Q value. I'm going to simplify it, and then you have this Q value plus where this Q value is actually a reward. So let's say reward, current reward, and you just say in the future, another reward, but from the future, that is the maximum that you would get. It's the maximum reward. So that's the other parameters like weight and all that. They're just, they control how much you update the reward over time, like a learning rate in a sense. But this is essentially what's happening. So the Q value, it's a reward. You take the original reward and you kind of add to it the future reward. Given the next state that you get from the prior state, and you just, the table is learning rewards over time, so there you just pick the highest one, essentially. And that's the formula. So that's the Bellman equation formula, and we will see how we can do that. Now, this can be implemented also. This is kind of like the manual table approach, but this can also be implemented with a neural network. So that's, the idea. And the Bellman equation is still used in the neural network approach. Okay. All right. So these values can be looked up. And so now I think we can just start going over the code, essentially. So the code is described here in this Jupyter notebook, and I'm going to just go over it. All right, so let's go to the GitHub. So I have this one here. Right, so this example that I have here is with a neural network. So we'll try it. But first, let's try to do this manually. So I'm going to go back to my text here. So if you notice, I've broken this down into Q-learning using a table. And then after that, I have Q-learning using a neural network. Okay, so this is what we're going to try to implement right now. So let's start with Q-learning with a table. So should be that there's the for loop. Yeah, so that should be it. All right, so let's go ahead and try it. And I think Jim might be one of the issues. So let's see if I probably don't have that installed. So I'm gonna rename this. I'm just gonna say, oops, sorry. Rename. I'm gonna rename this RL, just lookup table. Lookup table. Okay. Save it. I'm just gonna delete these two things. And I'm going to add my library. So I'm going to run NumPy should be there, but NumPy is not there either. Okay. So pip install NumPy. Okay. Right. These are warnings. Let me run it now. Right, so it found NumPy now, but not Jim. So let me do pip install Jim. Okay. So hit run. Okay, so it did it. All right, so now the code should not be that long, but I'm gonna grab it from here. So let's see. I need to have this idea of a game, okay? So some environment because you need to simulate it essentially. So I'm gonna simulate the frozen game gym. So what you do is gym.make frozen lake, and then that returns an environment. So if you remember, at some point in the lectures, I did I did an environment of a GPT, or I did a code, code example of a GPT in an environment, some time ago. So it's kind of the same idea. Is what I was, sort of thinking about then. But this is just like this as a very simple example for us to understand. So I'm going to go ahead and hit run here, and it broke. All right, so let's try V1 instead. Okay. All right, so it didn't like V0, so now we use V1. All right, so now let's go back to the code here. The next step is to initialize the Q table. So what is the Q table? It's, this thing, remember, I'm just gonna, a very tabular approach, no neural network. Okay, so the table is gonna be 16 by 4 because the grid has 16 possible positions. So the state is very simple, a vector of 16, and there's 4 actions. Okay, so let's go ahead and do that. I can just copy this code here. Right, so Q table, np.zeros. We're going to say that the observation, so if we print this one, hopefully it'll say 16. Right, so we have 16 possible positions, possible states, and the number of actions should be 4. Okay, so the number of actions is indeed 4. So if we do this, let me actually... Oh. So I run this one here. That's the learning rate, which is just essentially how much I adjust the reward, how much, I'm going to have a reward, and how much do I add to that reward? A lot, very little. This is another type of like a learning rate also. And this is the number of episodes, which is how many times you play the game. So you're going to play a game, until you die or until you win. So it's essentially like start game 1, take several steps until you get to an ending point, then start another game. And every time you start a game, you want to randomize it also, so that eventually you do learn what actions you should be taking when you're playing the game. Guys, are there any questions? Okay, so actually somebody asked a question. All right, so someone is asking me, where is the Jupiter picking 16 and 4 without us passing it to that? Well, it comes from the fact that I'm using the Frozen Lake game. So you see, when I created an environment and told it that I was using Frozen Lake, it knows. Okay, it's like, oh, I know that game. It's got 16 states and 4 actions. Let's say, for instance, I said that I want to create a game of chess. Then it knows, oh, okay, that has how many, the grid is this size. I don't know, it's like 8 by 8 or something in chess. And it's got a king and a queen, and I know the rules of the game. That's why we do this, so that we don't have to code. Otherwise, this is literally coding a whole game and its rules. But by having something called Gym, we are able to do this. So for instance, to give you some context today, a lot of people are asking or are trying to create a gym for GPTs. A gym for GPTs where they can play in that environment and learn more about the world and about reasoning and so on. Did I answer your question?
Yes, you have, Prof.
Okay, great. All right. So yeah, so it comes from the game essentially. All right, so we've done that part. Um, Now we take 2000, we'll have 2000 epics and initialize some parameters L, R, and Y. Each episode represents a game played, as I said. Um, and then we'll have these lists that allow us to collect the number of steps taken per episode and the total reward per episode. And this is kind of to keep track of the performance that we have. So I can create that list here. Okay, so let's run these two. Now the Q table also, let's just print out the shape so that we can see that it is in fact 16 by 4, and you can see that there. So this, as you can see, it is currently made up of all zeros, okay? But we need to add more values to it, or we need to learn these values essentially, okay? Right. So we've got that part done. And now, as you can see, this is essentially the entire code. So I'm going to grab it. That's the whole Q-learning algorithm. We can take a look at it here. Once it finishes, well, I'm going to describe it, obviously, but I just should be. Okay. So I have my GitHub. Take a look. So we do the main loop. All right. So anyway, let's just run this part. Let's see if it breaks. Okay, invalid syntax. I guess I'm missing some variables. J may have missed them. Okay, I may have missed that variable. So J is probably 0. So let's just add it here. Okay. Let's try it again. Uh, I'm gonna have to go one by one here. So let's see. So the logic is for I in range num episodes. So we're just gonna play a game. So every time we play a game, we reset the game to start, and it's gonna give us a starting position. So if you notice, it says n reset gives S. So this S is essentially our starting position. RL is just going to be rewards that we're accumulating. D just means that the game has the game ended or not. So initially, when you started, the state is false. So it means that the game has not ended, whether you won or whether you died. J is just, as you can see, is just a little variable so that we can take a number of steps. So what this means is in this first for loop, we start a game because we reset the game. Just give me a sec, guys. My battery's low. Okay. So should be fine now. So we start a game, and then in that game we have like 90, 100 plays. You know, like if you're playing a game and you can roll the dice 100 times, for instance, something like that. So you can take 100 steps in that game before, because you can be in an infinite loop, right? So you want it to end at some point. So once you take your first step in the game, you increment J, which is the steps. You're going to then here, what do you do here? This is the number of actions that you have available, Z. So because you look at the environment n action space dot n. So this should be 4, the number of actions. This function here is probably like the most complicated to understand, but essentially it's trying to select a action to take. So if you notice here, what it's doing is, and let me kind of like break this out a little so it's a little bit easier to read. I'm gonna do that, right? So essentially you grab a vector, move this over here. Actually, I can do this randomness val, and it's going to be this whole thing here. Okay. So now this is easier to visualize, right? So there's just that. Okay. So now we can probably just move this up also. So what's happening here is you need to pick an action from the Q table. So the Q table, you need to select to tell it what state you're in. Well, what state are you in? You're in the first state, when the game started. So you plug in that state into the Q table, and notice, if you remember from slicing in NumPy, what you're doing there is you're grabbing the vector with all 4 values. And then you use the function argmax, so that argmax will return the index of the highest value. So let's say that, so it's essentially like looking at, oh, where is it? It's essentially like looking at the table we had here, right? You're at this state, and you look at these values, and you return the index of the highest value. So that's 0.8. So it's action down, or if it's encoded as 0, 1, 2, 3, then it would be 1. So 1 equals down. Okay? So that's what this does, essentially. So you take from that vector the maximum value. But you also have this value, randomness. What randomness does is it's going to add some randomness to all 4 values in the vector. And why do you need that? You need that because in the beginning, these values are zero, right? So if you remember in the beginning, you haven't actually learned those values. So they're just going to be all zeros. And because they're all zeros, you can't really, uh, there's no maximum of 4 zeros, right? They're all zeros. So by adding a little bit of randomness to each one in the beginning, then what you accomplish is that you are able to select one randomly, essentially. Okay, so that's what you're doing. So you select one randomly. The amount of randomness that you add to the vector is controlled by this value here, which is controlled by the game, I. So what this means is as in the beginning, the amount of randomness that you add is a lot, but towards the end of the number of episodes, you're adding very little randomness. So initially you could conclude in the beginning, you're relying on this heavily, the amount of randomness that is being added to the vectors, but by the end of the episodes, you're trusting more this, and this is essentially almost zero. Does this make sense, guys? This idea? Any questions? This is probably one of the hardest parts. All right, so I'm not hearing any questions. So it's 7:04. So let's take a 10-minute break. So I'm going to end this session right now, and we'll come back at 7:14 and just continue the second half of today, which is, like I said, just, reinforcement learning. This is where I like to start with reinforcement learning as we are leading up to reinforcement learning through human feedbacks, okay? All right. So I will end this session and I'll come back at 7:15 so that we can continue the lecture. All right.